So here we will continue with our introduction to logistic regression. Again, remember that with logistic regression we're modeling the risk of some response, disease or death, or we might want to describe the differences between success and failure. So we always have a binary response, a 0, 1, yes, no, success, failure response. Sometimes we want to predict probabilities that a randomly selected individual will fall into one of two categories of the binary response as a function of some explanatory variables. And sometimes we want to classify new students. So this is another form of prediction. We want to classify new individuals into either a success or failure given the explanatory variables. So those are some uses of logistic regression. So we'll start off talking about simple logistic regression. And remember, simple, as with linear regression, just means one x variable. So we're starting off simple here. And some notation I'm going to use is I'm going to let P of x. So P stands for probability, and x is going to be the probability. So the probability that the response variable equals 1 or success when x takes on a certain value. So the probability that y equals 1 is going to depend on x. So this is the notation that I'll use throughout. And we can define the simple logistic regression model in 3 different ways. And I already hinted at these as we were building up to logistic regression in the last set of notes. So we can look at the log odds version of the model. So remember that the logit is just a fancy name for the log odds, or if I write it in math terms, it would be the natural log of the odds. Okay, that's that logit function. So it's just the log of p of x over 1 minus p of x, which is just our linear function in x, beta 0 plus beta 1x. Okay. We can exponentiate both sides. If we take e to the both sides, exponential of log cancels out, so we just have p of x over 1 minus p of x. This is the odds at x. And then we just exponentiate the linear function, e to the beta 0 plus beta 1x. We can also turn that into a probability, and we saw how to do this in the last set of notes. If we take, so you can prove this for yourself if you want to, but remember this formula. Odds is equal to p over 1 minus p. Right? You can solve that algebraically, just like we did in the last set of notes, to show then that P is equal to odds over 1 plus odds. So again, if I gave you something like the odds are 3 to 1, we could put 3 over 1 plus 3, or 4, so 3/4, the P would be 0.75, just like we showed in the last set of notes. If the P is 0.75, the odds would be 3. So here's a simple formula that you should remember to convert between odds and probability. And that's exactly what we showed in the last set of notes. We solved this algebraically last time. That P is the odds over 1 plus the odds. So now, what can we do with that? So in our simple logistic regression model, we have a slope and an intercept, just like we do in a simple linear regression model. And we have to be careful in interpreting them here, because now we have three different forms of the same model. We have the log odds form, the odds form, and the probability form. So our interpretation will take on slightly different meanings if we're thinking in terms of log odds, odds, or probability. For the log odds model, we're going to interpret the slope and the intercept as usual. That is, and by as usual I mean similar to a linear model. So if you know how to interpret slope and intercept in a simple linear regression, you'll be in good shape here. But now the response is the log odds. So we model changes in the log odds as the value of x changes. So the intercept, which remember I'm putting, if x is equal to 0, I'm going to use the notation p of 0. So that'd be logit p of 0. That's just going to be beta 0. If I plug 0 in for x, the beta 1 terms drops out and I'm left with beta 0. So that's the log odds of y when x is equal to 0. Is this interpretation useful? Well, log odds is a tricky concept, so I'm going to say not particularly. As you'll see, we'll have more useful notation, or we'll have more useful interpretations of the intercept and the slope. The slope, just like in simple linear regression, the slope is interpreted as for every 1 unit increase in x, the log odds of y equals 1 changes by the slope beta 1. Again, is that useful? Not really. Okay. This is not really useful interpretation, but that's where we start in logistic regression. But we get more useful interpretations when we switch into both the odds or the probability model. So remember, for the odds is always p over 1 minus p. And so if we want to interpret the intercept is when x is equal to 0, so that'd be p of 0. So the odds would be p of 0 over 1 minus p of 0. And remember that we can get to the odds by exponentiating your linear function. We showed that on the last page. So if I want to interpret the intercept on the odds scale, I just take e to the beta 0. And the interpretation is the odds of y equals 1, that is relative to y equals 0. So what are the odds that y would equal 1 when x equals 0? Odds themselves are still tricky to interpret, but I'll show you an easier way to interpret odds down below. Actually, when we talk about slope, we're going to get into this a little bit. The slope, remember, the slope on the log odds model is for every 1 unit increase in x, the log odds changes by the slope. The log odds of y equals 1 changes by the slope. So let's look at this as a 1 unit increase in x. The odds when x is x plus 1 over the odds of x, we can write this in terms of, so the odds when we're using x plus 1 is p of x plus 1 over 1 minus p of x plus 1. The odds when we're using x is p of x over 1 minus p of x. That's equal to e to the beta 1. Okay? Or another way of thinking of that is that the odds of x plus 1 is multiplied by the odds of x times a factor of e to the beta 1. So let me break that down here a little bit. And this is actually what we call an odds ratio. A ratio of odds as we increase by 1 unit of x. So it's a ratio between odds. Odds ratio is a ratio between odds. That's deep. But when we're thinking about a continuous or a quantitative predictor, x, we can think in terms of a 1 unit increase in x. So that'd be the odds when x is x plus 1 compared to the odds when we're just thinking about x. So let's write this out. If we have x, the odds at x, remember, is p of x over 1 minus p of x. Remember that to get to the odds scale, we can just exponentiate the linear function. So that's e to the beta 0 plus beta 1 times x. And if you remember your math classes, talking about the exponential function, e to the beta 0 plus beta 1x, when you have a plus in the exponent, that means we can really break that out as a multiplication problem. E to the beta 0 times e to the beta 1x. If you have to review your exponential functions, this might be a good time to do that. So if, on the other hand, we're talking about x plus 1, 1 unit increase in x, that would be p to the x plus 1 over 1 minus p to the x plus 1. And this is not a multiplication problem. This is a function. So we're looking at p as a function of x and p as a function of x plus 1. But again, we can write out our linear model, but now x is equal to x plus 1. Okay. So again, I can write that out as, first I'll just do a little algebra on the exponent and say e beta 0 plus beta 1 x plus beta 1. I just multiplied this out. And again, we have a sum in the exponent, so we can break that apart. We can factor that as e to the beta 0 times e to the beta 1x times e to the beta 1. Okay. So this is my formula for the odds when I plug in x plus 1 into the linear model. So if I want to look at the odds ratio, so the odds ratio for a 1 unit increase in x, that would be the odds of x plus 1, or the odds at x plus 1, I should say, over the odds at x. This is the odds ratio for a 1 unit increase for a 1 unit increase in x. Right? Well, now I'm just going to plug in what we have here. The odds at x plus 1 is e to the beta 0 times e to the beta 1x times e to the beta 1. The odds at x are e to the beta 1 0, or e to the beta 0, sorry, times e to the beta 1x, and that's it. So now it's a division problem. E to the beta 0 over e to the beta 0 cancels out. E to the beta 1x over e to the beta 1x cancels out. That simplifies to e to the beta 1. So this is interpreted as the odds ratio for a 1 unit increase in x. And this might take a little while to wrap your brain around this. You might need to think about this, but I want to tell you that the odds ratio is definitely the most used interpretation when it comes to logistic regression. So this is the most important interpretation of slopes in a logistic regression. I'm going to highlight this. This is the most important interpretation of slopes in a logistic regression, is the odds ratio. Okay. And we'll see that a lot. So let's take us to the next level and talk about the probability model. So remember, we can interpret these models in terms of log odds, not particularly useful as an interpretation because it's difficult to understand what log odds means. We can talk about it in terms of odds, which we usually convert to odds ratios. And we can talk about it in terms of probability. So remember that probability is just equal to odds over 1 plus odds. That's just a formula. That's a conversion between probability and odds. So, since we know that the odds, if we're thinking about the intercept on the odds scale, the intercept is e to the beta 0. So if we think about on the probability scale, we just take the odds over 1 plus the odds. So this is the probability when x is equal to 0, the probability of y equals 1, whatever y is, our response variable, the probability of y equals 1 when x equals 0, is e to the beta 0 over 1 plus e to the beta 0. For the slope, it's actually a little difficult to give a general interpretation of the slope. One thing you can always do, of course, is once you have your linear model, once we have e to the beta 0 plus beta 1x, we could definitely plug that whole model into the probability formula or probability conversion, which we'll do below. But for the slope itself, it's a little difficult to interpret the actual number. But instead, it's easier to interpret just more generally using the sign. If the sign is positive, if we have a positive slope, then the probability that y equals 1 increases as x increases. If we have a negative slope, you'll see that it decreases, or maybe we have a flat line. So let's look at this a little bit. It's difficult, as I said, to interpret the actual number of beta 1 on the probability model, on the probability scale. But what we can think about is, if beta 1 equals 0, just like in a simple linear regression, that basically means that we have a flat line. So my colors didn't come out here, but this is my black line. So if beta 1 equals 0, then the probability that y equals 1 is constant and doesn't change. It doesn't depend on the value of x. If beta 1 is greater than 0, this is my red line. So if beta 1 is greater than 0, then the probability that y equals 1 increases as x increases. So we have this S-curve, and the probability usually looks like this S-curve because notice that it bottoms out at 0 and it asymptotes at 1, right? Probabilities have to go between 0 and 1, so we would have this S-curve that increases as x increases. If beta 1 is less than 0, so if we have a negative slope, then we have this blue line. And again, it's a backwards S-curve. It starts off at 1 for small values of x, for negative values of x. And it curves down to 0 as x increases. So these are the three different possibilities of interpreting slope on the probability scale. Again, I wouldn't interpret the actual number. I would try to just interpret what you know about the shape of the relationship between the probability and x, and we'll essentially have these three different shapes. So I'm going to pause it here and move on to the next video.